Okay, so now this is the last part of matrices. This is the last exercises that we'll do, guys, and we're done. So this part here of transition matrices is where we use recursion. So we're back to recursion now. We're using recursion to generate step-by-step matrices. So we're going to start off with looking at the car rental problem that we started off with at the start. So the car rental firm was the one that was in Bendigo and Colac, if you remember that one. So the car rental firm now plans to buy 90 new cars, and 50 will be based in Bendigo and 40 are in Colac. So given this pattern of rental car returns, the first question the manager would like to answer is, if we start with 50 cars in Bendigo and 40 cars in Colac, how many cars will be available for rent at both towns after 1 week, 2 weeks, 5 weeks, 10 weeks, 50 weeks? So we need to know where the cars are going and roughly find out. And we do this through a step-by-step recursion. So let's have a look. Constructing a matrix recurrence relation. So every recurrence relation needs a starting point. So our starting point here was that 50 cars in Bendigo and 40 cars in Colac. So we have to start off with something called an initial state matrix. So initial state matrix starts off with some notation called S of O. And in this situation, our S of O in this was 50, 40, like that. So it looks like this one here. So generating S1. So S1, initial state matrix is SO. S1 would be after 1 week, S2 would be after 2 weeks, so on and so forth. So to find out the number of cars in Bendigo and Colac after 1 week, we use the transition matrix. Our transition matrix is the original one that I showed you previously. Do you remember the diagram? So that one, our initial transition matrix was 0.8, 0.1 over here, 0.2, and 0.9. So that was our initial transition matrix. I shouldn't have said initial, but our initial state matrix is 50, 40, and the first transition matrix that we started with was this one. So now we need to generate the sequence for S of 1. So in order to do S of 1 starts off like this, your transition matrix multiplied by the initial state matrix. And in this situation, it would be this one here, 0.8, 0.2, 0.1, 0.9 multiplied by the initial state matrix, which was 50, 40 to get 1. Easy. Showing working out like I showed you before, you do that, multiply and plus, like that to show the working out. But there's your working out there. And when you dump that into the calculator, I want you to dump those two into the calculator there, press enter, and you'll get your answer as 44 and 46. So after 1 week, we'll predict, don't forget we are predicting here, that there'll be 44 cars in Bendigo and 46 in Colac. Simple. Generating S2. So for S2, it would be your transition matrix times S of 1. So the initial transition matrix, which is that, you got the answer previously there, and then you dump that into the calculator and you get that one. Simple. After 3 weeks, again, S of 3 will be T, S of 2, S of 4 will be T, S of 3, like that, so on and so forth, and you get your answers, and you can give the answers for that one. So after 3 weeks, there will be 36.9 cars. Obviously, guys, you can't have 36.9 cars, so there'll be 37 cars there and 53 cars over here. So round them off, obviously, that's 0.1, that's 0.9. One has to be there. So pretty straightforward in generating those. But what happens after n number of weeks? 50 weeks, 70 weeks, whatever. You can see that there's a pattern here happening. Look at this. S of 1, TSO, S of 2, TS of 1, S of 3, TS2, S of 4, TS3, blah, 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 like this, right? So in more general terms, S of n plus 1 equals TS of n. And that is the rule that you use for any week. Doesn't matter. So you use this rule as a starting point. That will give you a recurrence relationship, so we can model for any one that we want to do. So any number of weeks or days or whatever. And don't forget that S of O is our initial value. Right, let's have a look at this example. Using a recurrence relation to calculate state matrices step by step. So the factory has a large number of machines. The machines can be in any one of two states, operating or broken. Broken machines are repaired and come back into operation. Sound familiar? We've already done that. At the start, 80 machines are operating and 20 are broken. So automatically at the start, I have 80, 20. There we go. And now we know for any number of weeks or days or whatever they're operating or not, we've got to set up our transition matrix, which was given to us previously, and that was 0.85, 0.15, 0.05, and 0.95. There's our transition matrix. I've got my initial here too. What else do I know? I know that S of n plus 1 equals T S of n. So now it says determine the number of operational and broken machines after 1 day, after 2 days, after 3 days, whatever. Easy. Again, we start off with these two here, right? So if I had to find S of 1 is going to equal T S of O, which means this one multiplied by this one. Dump it into the calculator and you get your answer as being 69 and 31, operating and broken. So the next part of this question is for 3 days. So we need to find out how many are operational after 3 days. So that means we've already done this one here. We know after 1, after 2, S of 2 is going to be T S of 1, and we know that S of 3 is going to be T S of 2. Again, you put them into the calculator like so, and you know that after 3 days, we've got 53 machines there and 47 machines here that are broken. So it's quite easy. It's calculator work, step by step, for 3 days. A rule for determining the state matrix of a system after n steps. So our initial value, we know S of O, and we know our rule, S of n plus 1 equals T S of n, to generate the matrices step by step. So if we follow through the process of step by step, we have our initial state matrix, S1 equals TSO, which you've done before, S2 is TS1, S3 is TS2, blah, 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 blah. We've done this. Continue on this process. S of 4 equals T to the power of 4, S of O. S of 5 equals T to the power of 5, S of O as well. Why is now have we introduced powers? Because have a look at this. Have a look at this. S of 2 equals T S of 1, which means it's the same as saying T times T S of O, isn't it? See this? That's where you get T squared from. T times T is T squared. Okay, and then you can see that here where the t cubed comes in. So more generally, if we're talking about n, trying to find n, use the formula S of n equals T to the power of n S of O. That's what I want you to use for n steps. So it's the same rule, but because of the t's like this, see this spread here, that's why it works that way. So that's what we're going to use for whenever we see n and you've got to find n and whatever, we're going to do that. Right. Example. The factory has a large number of machines. The machines can now be in one of two states. Again, we're going operating or broken. Broken machines are repaired and come back into operation and vice versa. Initially, there are 80 machines and 20 are broken. We've got our initial, we've got our transition. Determine after 10 days. Simple. It's n, yeah? N is equal to 10. That's what we've got to remember here. So what we are doing in this situation is using the rule S of n equals T of n S of O. So S after 10 days equals T to the power of 10 S of O. So that's your T over here. and you've also got your S of O here. So you input that into the calculator, you know, when you set up your matrices. And then right at the end, you just write down t to the power of 10 times, you would have called that S, times it by S, and it will spit out your answer for you, giving you S of 10, which is 31 and 69 machines. Very straightforward. When you're using, like if they're not going after the other, okay? Now we get to an area called the steady state solution. So let's go back to the Bendigo-Colac situation, right? I don't want you to worry too much about this here, but we will talk about it. The question is, will the number of rental cars available from each location vary from week to week, or will they settle down to some fixed value? So what they're saying here is, in Bendigo and Colac, at some stage, will they settle down where you've got, you know, we started off with what, 50, 40, 90 cars. Would I get to 45, 45, or a steady state solution where it won't change? Okay, so that's what they're saying. So in this situation, you notice if we did it, initially we had 50, 40, then it went to 44, 46, then it went to 39, 39.8, 50.2. Can you see this? So after 3 weeks, between 4 to 11, look what happens up here. Look at this after 12 weeks, right? Look, after 12 weeks, this is getting closer to 30. This one's getting closer to 60. Can you see? So this now tells me there's going to be a balance of 30-60 after 20 weeks, 30 weeks, 40 weeks, 50 weeks. We're going to get to something called a steady state solution. So what's the point of this? How do you get to a steady state solution? So we'll have a look at doing something like this. So here it just shows you graphically when you've got your cars at Bendigo and cars at Colac in this graph over here, right? So as we as the weeks go on, the number of cars of each location start to settle down. You're not going to get a split 50-50, but it settles down to something called your steady state solution or equilibrium. So for the rental car problem that we've been talking about, in practice, 30 cars at Bendigo and 60 cars in Colac, which means that's where the steady state solution will be. Okay, so you can have a look here. See the graph, how it goes like this. They intersect at some point, but we get to a steady state solution round about there. Okay, so in summary, even though the number of cars returned to each location vary from day to day, the number at each location will eventually settle down to an equilibrium or steady state solution. Important. In the steady state, cars are still moving between Bendigo and Colac, but the number of cars rented in Bendigo and returned to Colac is balanced by the number of cars rented in Colac and returned to Bendigo. Because of this balance, the steady state is also called its equilibrium state. For a system to have a steady state, the transition matrix must be regular and the columns must add up to 1. Important. A regular matrix is one whose powers never contain any zero elements. So in practical terms, this means that every state represented in the transition matrix is accessible either indirectly or directly from every other state. Simple. Right. A strategy for estimating the steady state solution. In the car rental problem for Bendigo and Colac, we found that even though the number of cars returned to each location initially varied, from day to day it settled down. Although we arrived at this conclusion by the repeated calculations, we can arrive at the solution much faster by using this rule. S equals TNSO to find the steady state solution, because N tends to keep going to infinity. Okay? So let's have a look at this situation. For the car rental problem, S of O is 50-40. That's the transition matrix. Find the steady state solution by calculating N for that, and that. We've got to do this 4 times. So initially in the calculator, you dump that into T, that into S, correct? And I'll put it to the power of 10. So you would just be asking the calculator, do T10 for me, S of O, or S in your situation. So let me just rub that out. So you got T10 S. You would also do T15 times S once you've inputted them in as a matrix, yeah? Then you would do T17 times S. And the last one you do is T8. So it's just graphics calculator work to get to the steady state solution. What do you notice? 30, look at this, 3060, see 3060? So really, if you're ever going to find the steady state solution, N can be found anywhere between or greater than 15 and above as a sort of as a rule for us. Can you find the steady state solution for something? Yeah, about 15 will do it for anything anyway. So you'll see that the numbers tend towards getting closer, like in this situation, 30.1 and 59.9. You already know what the steady state solution is from there. But if you did 25, T25, you're still going to get around here as well. Okay? So use 15 as a guide. Okay? That's what I want you to do, is just use 15 as a guide to find the steady state solution. Right. And this bit here, transition matrix modeling using the rule S of n plus 1 equals T S of n plus B. So to date, we've only considered of the form like this. That model, this recurrence model can be used to model situations where the total number of objects in the system, like cars and machines, people and birds, all remain unchanged. For example, in the car rental problem, we had 90 cars available for rental. But what happens if the management wants to increase the total number of cars available by rent by adding an extra car at each location a week? So we've got a new system here where we're adding extra stuff, extra cars in this situation. So the initial state matrix was your S of O. S of n plus 1 equals T S of n, where B is now a column matrix. So the next examples we're going to look at is for the car rental problem. Right, a rental firm starts with 90 cars, 50 located at Bendigo and 40 located at Colac. Cars are usually rented between each town. However, a small percentage of cars rented in Bendigo are rented in Colac and vice versa. Previous question, and that's the diagram. We've already seen this diagram here. To increase the number of cars, 2 extra cars are added to the rental fleet at each location each week. The recurrence relation that can be used to model the situation is this. So we know that our initial state matrix is 50-40. The transition matrix was 0.8, 0.2, 0.1, and 0.9. So don't forget, I had Bendigo and Colac, haven't I? Right? Now they're saying that they want to add 2 extra cars to the rental fleet at each location. That means at Bendigo and Colac. 2 at Bendigo and 2 at Colac, giving us this column matrix B. Right there. Okay? So now it says determine the number of cars at Bendigo and Colac after 1 week and then after 2 weeks. Same situation, except for in this situation I am using S of n plus 1 equals T S of n plus B, which is now this part. Okay? So for your S of 1, that's going to be T S of O plus B, isn't it? So that's going to be just the transition matrix, which is 0.8, 0.2, 0.9 down there, 0.1 there. That's your T. Your initial state matrix was still 50-40, but this time we are adding at each location 2 and 2. Just like that. So you've got that in the calculator, you've got that in the calculator, and that in the calculator, and all you would do there is T times S plus B. You type that into the calculator, press enter, and then you'll get 46 and 48. So that's how that situation works there. But don't forget, they ask you in English, you've got to answer in English as well. We predict that there will be 46 cars in Bendigo and 48 cars in Colac. Okay? Now, the next part of the question says for 2 weeks, exactly the same steps, but you've got to show the working out, yeah? S of 2, I'll just do it up the top here, equals T S of 1 plus B. Put that stuff in. Remember, don't forget to do your lines that we're multiplying and adding here, and we're also adding it to that column there too. And then you can get the answer for S of 2 just by using your graphics calculator, but you're still showing the working out. Guys, that's it. Now do 12C all exercises and 12C part 4 all exercises. Don't forget, this is the end of your Year 12 Further Mathematics course. It's been cut down. That's it. We are done. We now do all of the questions, the Chapter 12 review, the Chapter 12 summary, and we start to, I'll talk to you on the Zoom meetings as well, Mr. Maria and I, and we'll start doing revision for our final VC exam, and that's the course all done, complete. We are finished. Take care.